Welcome to this presentation on graph representation. Graphs are a crucial part of computer science, appearing in social networks, roadmaps, web crawling, and even AI algorithms. But before we can use graphs efficiently, we need to understand how to store and represent them in memory. In this video, I will cover different ways to represent graphs, the adjacency matrix and adjacency list methods, their advantages and disadvantages, a coding example showing how to implement both methods. By the end, you will understand which method is best suited for different scenarios. Let's get started. Graph representation methods. Before we get into the details, let's define what a graph is. A graph consists of two main components. First one is nodes, also known as vertices. These represent objects like people in a social network. Second one is edges. These are the connections between the nodes representing relationships or links. Graphs can be of two types, directed graphs and undirected graphs. Directed graphs where edges have a specific direction, like a one-way road. Undirected graphs, on the other hand, where edges don't have a direction, like two-way roads. Now, how do we store a graph efficiently? There are two main ways, adjacency matrix and adjacency list. Adjacency matrix uses a 2D array. Adjacency list uses a list of linked lists. Each method has its own pros and cons, which we will explore next. Let's first talk about the adjacency matrix method. An adjacency matrix is a 2D array where each row and column represents a vertex. If there is an edge between two vertices, I and j, we set matrix ij equals to 1. If no edge exists, we keep it as 0. For example, if we have a graph with 3 nodes, if node 1 connects to node 2, we set matrix 1, 2 equals to 1. If there is no connection, we leave it as 0. This method is easy to implement but takes up more memory, especially for large graphs. Let's now compare the pros and cons of adjacency matrices. Advantages are adjacency matrices are fast edge lookups. Checking if an edge exists takes O1 time because it's a direct lookup in the matrix. Easy to implement. Since it's just a 2D array, it's simple to manage. Some disadvantages are consumes too much memory. It takes OV squared space even if the graph has very few edges. Inefficient for sparse graphs. Since most of the matrix will be filled with zeros, we waste a lot of space. In short, adjacency matrices are good for small, dense graphs, but not for large graphs with fewer connections. Now let's look at the adjacency list method. Instead of a 2D matrix, we use a list of neighbors for each vertex. If a vertex has edges, we simply list the connected vertices instead of storing an entire row of zeros. You can see an example in the slides. This method is much more memory efficient because we only store existing edges rather than filling up a huge matrix with zeros. Just like adjacency matrices, adjacency lists have their own strengths and weaknesses. Some advantages are it uses less space. It only stores existing edges, making it efficient for large sparse graphs and faster traversal. Since we only store necessary edges, graph algorithms like BFS and DFS run faster. Some disadvantages are its slower edge lookups. Checking if an edge exists takes OV time instead of O1 like in an adjacency matrix. And it is not ideal for dense graphs. If the graph has too many edges, adjacency lists take up a lot of space. Adjacency lists are best suited for large, sparse graphs, but may not be the best choice when we need fast lookups. Now let's compare adjacency matrices and adjacency lists. Adjacency matrix works well when the graph has many edges because lookups are fast, but it's not memory efficient for graphs with few edges. On the other hand, adjacency lists work well when the graph has few edges because it uses less memory, but edge looks up are slower, making it less suitable for certain applications. Now let's talk about how to implement graphs in code. To represent a graph, we can use a 2D array for an adjacency matrix, a dictionary or linked list for an adjacency list. We will implement a graph using an adjacency matrix and a graph using an adjacency list. So let's go to coding. Okay, this is the first method of representing a graph using an adjacency matrix. You can see my code here. I began by defining our graph matrix class here. Inside the class, we declared two variables. First one is matrix and second one is vertices. Matrix variable is our 2D array that will store all edges. Vertices variable keeps track of the number of nodes in the graph. Next, I created a constructor that initialized our graph, and I assigned the number of vertices using the size parameter. Then I created a 2D array of size, automatically setting all values to 0. At this point, this graph exists, but it doesn't have any connections yet. Next, the addEdge method here takes in two numbers, source and dest, which represent the starting and ending nodes of an edge. First, we update matrix source dest equals 1, meaning there is a connection from source to dest. Since our graph is undirected, we also update matrix dest source equals to 1 to reflect the reverse connection. This means that if there is a bidirectional edge, both values will be set to 1. Now let's define the display method, which prints the adjacency matrix. I loop through each row and column in my matrix here. For each value, we print either 1 if an edge exists or 0 if no edges exist. Finally, I can print a new line after every row format the matrix properly. In the main method, I first created a graph matrix object with 4 vertices, then add edge between different nodes to form a connected graph. Finally, I call display method to print the adjacency matrix, allowing to visibly check the connection in this graph. Okay, let's see the output. Let me run this code. Okay, here is the output. This output shows how nodes are connected. For example, node 0 is connected to node 1 and 2. Node 2 is connected to node 0, 1 and 3. Now let's move on to the adjacency list method. This is my Java code for adjacency list. Here I declare an array of linked lists called Adjacency. Each index in this array represents a node and it stores a list of all the connected nodes. In our constructor here, we initialize the ADJ list array with a size equals to number of vertices. Then we loop through each index and assign it an empty linked list. Then the addEdge method works by simply adding the destination nodes to the source nodes list. Since this graph is undirected, we also add the source node to the destinations list, creating a two-way connection. To print our adjacency list, I loop through each node and print its connected nodes. This makes it easy to visualize the structure of the graph. Okay, now I'm going to run the program. This output shows how each node points to its connected nodes in a list format, making it much more space efficient and easy to understand than an adjacency matrix. So final thoughts here are, adjacency matrix is best for dense graphs where we need fast lookups, and adjacency list is better for large sparse graphs where memory efficiency is key. Alright, let's summarize everything we covered today. Graphs can be represented using an adjacency matrix or an adjacency list. Adjacency matrices are good for dense graphs but takes up more memory. Adjacency lists are better for sparse graphs using less memory but making edge lookups slower. Choosing the right method depends on the graph size and structure. Alright. This video was created as part of a university project presentation. So I want to tell you guys, the focus was on explaining the topics rather than teaching coding in depth. Thank you for watching. If you found this interesting, feel free to leave a comment below. See you in the next video. Thank you.